I'm at 450 newtons below the line. I asked the guy right above me what he'd like to do. He says, I'd like for you to pop up in the air instantly, 1,350 newtons higher than you used to be. Since I started 450 newtons below the line, 1,350 newtons puts me 900 newtons above the line. As I move from C to D, I cross an area which is a rectangle. Again, that rectangle up there is equal to base times height. That base is 3 meters big. The height is 300 newtons per meter. And so the area involved is 900 newtons. Now you can also tell which way to go very nicely. In other words, you'll notice the reaction today tells you he wants that curve to jump up. And you'll notice all these little arrows inside the block. They're little downward pointing arrows, so they want to go down, go down, go down, go down, go down. The R sub C wants you to go up, and the little arrows from C to D say to go down. So if we're going to go 900 newtons worth of area down, and we're 900 above the line, that makes it nice because these shear and moment diagrams should close on 0. You start on the left-hand end at 0, you work over to the right, and they should close on 0. Now then, we know there's a point 900 newtons and a point 0. The question is how we should connect the 2 points. We go to the mathematician. He says straight horizontal lines turn into straight sloping lines. So we simply connect the 2 points with a straight sloping line. Now at that time we cross something kind of weird, and it is a 2,700 Newton meter twist. But this shear diagram is for telling you up and down movements of the diagram only. It's only for shear. So even though the 2,700 Newton meters is at the end, I wouldn't care if it was at point B. As I crossed it, my shear diagram would not hop up, because that moment doesn't point up, and it wouldn't hop down because it doesn't point down. That's not to say that the 2,700 didn't affect the shear diagram, because the 2,700 affected the reactions, and the reactions greatly affected the shear diagram. So that torque, that twist, that moment did influence the shear diagram. It just does not make it kick up and down as you cross that concentrated moment. Alright, next thing I'm going to do is I'm going to go down and draw a bending moment diagram. Incidentally, that shear diagram is very useful. I can now tell you where the peak shear occurs. The peak shear is 900 newtons. I can assure you that one of the answers on the quiz will assume that you think 1350 is the worst shear, because that's the biggest force I see acting on the beam, 1350. It just so happens that the 1350 does not get into the beam. At first, it's 450 required just to overcome how far the shear diagram was below the diagram, and then it kicks the diagram up to 900, so the peak shear for use in the equation is 900 newtons. Alright, moment diagrams work exactly like a shear diagram. I mean, I wouldn't even know there was any difference in them, except this one says moment next to it. It is obtained by backing up one diagram and asking if you have any people who want to push up or push down. You calculate the area under the curve to find out how much he wants to go up or go down. In the shear diagram, we don't really have any little arrows telling us which way to go. So I'll just have to say that this area right here between A and B is a positive area. And the reason is because it's above the line. That area will push the diagram up. Next, between B prime is a triangle. It's also a positive area. It's going to push the diagram up. Between B prime and C is a negative area. It's going to start pushing the diagram down. And finally, this big area between C and D is going to push the diagram back up. Any concentrated moments will make the diagram jump one way or the other. Alright, here we go. The area between A and B is a rectangle, so it is its base, 3 meters, times its height, 450 newtons. So the area between A and B is 1,350 Newton meters. It's kind of nice that area has the units Newton meters, because he said he would tell us what to do on the moment diagram, and those areas have the proper units, Newton meters. I'll go ahead and calculate all the areas right quick. Area between B and B prime is 1/2 of the base, 1.5 meters, times the height. It's 450 newtons tall, and that area is equal to 337.5 Newton meters. Then I calculate the area for piece B prime C. Ooh, I cheated. Because the thing said this is 4.5 meters across there, it was pretty easy to figure out that was 1.5 meters. But that's not easy to do. That's X bar. That was one of the rules we laid out a minute ago. You can tell when this line crosses the axis by using the equation X bar equals 2. All you do is you take how high is the shear diagram, the starting value of the shear, and you divide it by who's pushing that diagram down. That's merely the load rate. Now that's back on page 15, that rule. The reason that works is because the shear diagram is at this time right here 450 newtons up in the air. The only reason it's going down is because the diagram above it has a bunch of downward little pointing arrows. Those arrows have a downward pointing intensity of 300 newtons per meter. So if you'll simply take 450 newtons initial height in the air divided by a guy who wants you to drop 300 newtons every time you move a meter, you'll figure out how long it's going to take him to get that curve down to 0. So you simply take the starting shear, divide by how fast it's being pushed down, the load rate, and that's 1.5 meters. Alright. So now I've got justification for calculating the area BB prime. Now I'm going to calculate the area for B prime C. It is 450 newtons tall, It has a base. Well, if this is 1.5 right across here, out of 3 meters total, this is also 1.5 across here. I'd simply subtract that from the total length, 1.5 meters. And the area factor of a triangle is 1/2. So that area is equal to another 337.5. And finally, the area of that big old triangle down on the end, 1/2 base height, 1,350 Newton meters worth of area. Now, the nice thing about calculating the areas now is you can add them all up and see if they close on 0. So you don't have to waste a lot of time plotting the next diagram, then find out you got a mistake on the area somehow, and the thing doesn't close, and then you got to go back and redraw it. If these areas don't add up to 0, I've got a problem. So the first area, Kelly Crankies for me if you would. The first area is plus 1350. The next area should push the curve up in the air another 337.5.
Okay.
The next area should knock the curve down 337.5 because it's below the line. And then the last curve should push the thing up in the air 1350, which equals 0.
Correct.
No, now you're supposed to say no.
Oh, excuse me. No.
But it's not 0, is it? What does your calculator say?
Well, 27.
2,700. Well, see, you've just drawn so many of these, you knew we were going to win in the long run. That's how you tell which way that concentrated moment jumps easy enough. I mean, there's a very firm and fast rule, and that is that a concentrated moment that looks like this makes the moment diagram jump down. But if you forget that rule, or if you can't find it in your notes somewhere, you just can't hardly go wrong, because you're destined to be off by the magnitude of that moment. And if you're off 2,700 in the air, well, there's no doubt what you want to do. You want to kick it back down to 0 when the thing closes. So you'll jump it down 2,700. All right, so now we're ready to draw the moment diagram because it is destined to close on 0. As always, we start on the left end of the beam and we work towards the right. That gives us the good sign conventions and keeps the little arrows so they tell us which way to go. The first area says, as you cover area AB under the shear diagram, I request that you end up 1,350 higher than you used to be. I plot the point 1350 on a piece of graph paper. The next thing is the question of how to connect the dots. Straight sloping lines in any diagram, straight horizontal lines in any diagram turn into straight sloping lines on the next diagram. So I know how to connect that. Next, I add the area between B and B prime. That area is calculated as 337.5 Newton meters. So I kick the diagram up in the air 337.5 higher than I was. That brings the total up to 1687.5. Now, there is a question on how to connect the dots between B and B prime, and the reason is 2 parabolas would actually fit between those 2 points. And I have trashed this diagram so badly, there's not hardly room to show. Let me stick another one in here. Between these 2 points, it is possible that the lower parabola might be the proper parabola, the one that has concavity up, as opposed to the one that appears to be concave down. Now, if you're just looking for the peaks, it probably doesn't matter. You don't have to spend a lot of time worrying about which way it goes. Not only that, this moment diagram is the end of things. We're not going to the next diagram. If we were going to the next diagram, I'd be very interested in which way that curve goes, because the area would be different. Every now and then you'll find that kind of a curve comes up on your shear diagram, so you really should know how to tell whether it's the high part of the curve or the lower curve. You do that by, again, the mathematician tells us that the value on any curve up here predicts the slope exactly underneath that point down here. The value on an upper curve gives you the corresponding slope on the bottom curve. Now, if you'll look at point B prime on the shear diagram, the value is 0. Therefore, on the next diagram, it is necessary that you draw a curve having 0 slope. And that says that the bottom curve wouldn't fit, because the curve coming into B prime, if you pick the bottom curve, it has a heck of a slope when it hits the end. You want the top curve, the one that has 0 slope on its end. So it's pretty easy to tell which curve using this rule right here. Value gives slope. All right, now we're ready to go ahead. This point doesn't show a value, we'll calculate it. We are now 1687.5 Newton meters above the line. As we go from B prime to Charlie, we will subtract an area from B prime to C. That area was listed as 337.5, so we're back to 1350. As we go from C to D, we add another 1350 area from the preceding diagram. 1350 plus 1350 puts us 2700 above the line. You can tell which of these two curves is the proper curve. Here's my 0 value. That will tell me on the next curve where I should have 0 slope. That tells me the top curve is the one that I want. Now, there's been a couple of questions on the quiz, at least, we figure there is, because we look at 10 or 15 books that give sample quizzes, and I think these guys are, pretty much keep their finger on what's going on, where just the shear diagram has been asked. They should draw me a shear diagram for this case. So you probably, on the morning session, where they actually look at it and grade it, you need to do that right. You need to make sure you didn't put that curve down. In the afternoon session, where you just circle a dot, it'll probably just say, what's the maximum moment? Well, don't worry about what this curve looks like. If he just wants a peak number, phooey. Give him the peak number and go on with it, and don't worry about what the curve looks like. It's not in your best interest to tell him if it doesn't show up on the quiz. Then the final thing is as you cross the concentrated moment makes the moment diagram jump down, and therefore the diagram closes on 0. Now, that's a lot of work, no two ways about it, and a lot of places you can make errors, but the number of problems that depend on shear moment diagrams, it was massive. They show up in footings, they show up in retaining walls, they show up in the concrete part, they show up in the steel design part, they show up by themselves. Just go do one. So I really think a little time invested in this part, this area, bound to serve you well.
An example that I ran across in the test was a caisson. you might be a little bit leery of problems like that, especially with retaining wall type structures. That's where I ran into where you needed shear and moment diagrams. There will be, the concrete retaining walls, and then also sheet piles, caissons, and things like that. That's where I ran into this type of a problem on the test.
And did you have that on there that time? That's interesting. Okay. All right. Now, hopefully, seeing how this is done, then another few examples. We won't have to really carry them out numerically. On page 17, let me go ahead and just give you the reactions here so you can check them. This left reaction was 15.5 kilonewtons. And the right-hand reaction turns out to be 22 kilonewtons. I guess that should be a lowercase k to fit the standards. You'll notice, basically, as you go across, you did what R1 told you to do. As you went across, you saw no loads, so you didn't do anything. As you ran across the 15 downward pointing arrow, you kicked it down 15 lower than it used to be. As you went across the beam, there were no arrows saying go up, go down, so you didn't do anything. Then when you got underneath this rectangle, you just went ahead and calculated its area. Its area will be 15 tall by 1.5 wide. And I don't have that written down. Kelly, what does that come out? 15 times 1.5 is
22.5.
22.5 is the area. And therefore this point should drop down from a half above to 22 below. That's a change of 22.5. That's correct. And then you connect the dots by saying straight sloping line. In the upper diagram turns into a straight straight horizontal line. I need to go back and read the rules there. Straight horizontal line turns into a straight sloping line. And so you simply connect the two dots with a straight sloping line. Then finally, the reaction of 22 kicks it back in the air. 22, it closes on 0. The next task we have will be computing this area, which will push the curve up. Computing this area, which will push the curve up. Computing this little x-bar distance right here. So we know how much area is underneath this little tiny triangle, and so we will know the base of this great big triangle. And knowing that base, we'll compute the area of a triangle, and that'll be used to calculate the moment diagram. And on page 18, that's all repeated. The first area pushes the diagram up. Straight horizontal line turns into straight sloping line. The next little area pushes the diagram up. That should be a straight line in there. It looks a little curved, but it's a straight line. Then the little tiny triangle adds a little bit more. And then the great big triangle brings it on back down to 0. Again, there are two parabolas which would fit between the two curves, the 2 points. It's pretty easy to tell which is which. Simply go to the point where there is no value, and that'll tell you where there should be no slope. That'll tell you this curve won't fit that requirement. Alright, and I will leave page 19 for you to tinker with. There's a whole bunch of good examples in your books because they know those are important too. Page 20. I'm going to do nothing more than just draw kind of what their shapes are. Won't actually put any magnitudes on there. Our shear diagram would start on the left end at 0. The downward pointing arrows would tell you that the next curve should go down. The 2 points should be connected up. Well, that curve is a straight sloping line. Straight sloping lines turn into parabolas. Could be this one. Could be this one. Going to be really important I tell which. Because if it's this top parabola, I'll be using 1/3 base height for the area. And that comes from the first night's notes, area under parabolas, areas under cubics, and where their centroids are. Turns out if it's this fat curve, then the area under the fat curve would instead be 2/3 the base times the height. So it really is important I know which one, because on this next moment diagram, that's going to throw the point off if I don't get the right curve. How I tell is I simply go up to the previous diagram and go to the point of 0 value. And on the next curve down, I plot a curve of 0 slope. That tells me it's the top curve. Tells me the bottom curve is wrong. Now sometimes everybody sees that instantly and they say, he sure does talk a lot about that. And then other times, you know, the people say, what? So if that doesn't make sense, give a holler. Alright, the area we'll be looking for is 1/3 base height. We will now kick the curve up 25 higher than we used to be, wherever that is. We don't know where that is. We're not going to really calculate the numbers. We're then going to push that diagram down, because the little arrows say down, 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 down as we move across. Then the 6 kip load will kick in and say go 6 lower, down. Then that uniform block will say push it down some more. And finally the right hand reaction will close it on 0. These areas are easy to calculate. If you like, you can break it up into a rectangle and a triangle. Some people just like to take the end areas and average their heights, the end heights and average them, just sum them together, divide by 2, and multiply that times the base. That'll work nicely. Moment diagram. Moment diagram starts on the left end at 0. It will go down 1/3 base height. That'll be a cubic. And maybe it's that one, or maybe it's this one. I don't even care, because it's not going to be used for the next diagram. I don't think I'd bother. If he asked me to draw it, I'll bother, because he'll probably kick me a few points if I don't get it right. So I go up here to the 0 value, and I come down to the next diagram and I plot 0 slope. That tells me again that the top curve is the correct curve, and this curve not starting with a 0 slope, rather ending with a 0 slope, is the wrong curve. Finally, that next area pushes the curve up. The last area will push the curve down, closing it on 0. Let me give you a hint. If this curve does not close on 0, 9 times out of 10, check your reactions. 9 times out of 10, you got the reactions wrong, and that's why the thing doesn't want to close. You very seldom make mistakes calculating areas and stuff like that. It's usually back at the beginning. All right, page 21 is more of the same. You can see we're paranoid with this stuff. Just a quick sketch. Left end at 0, push the curve down. How much down? 1/2 base height, because it's a triangle. It's either going to look like this, or it's going to look like this. I go to the 0 value end, and I come directly under that point and make sure the curve has a 0 slope. This guy here doesn't have a prayer of satisfying that requirement. Therefore, it is the lower of the two curves. Next, nothing happens. I go straight across. Next, I have a moment. Doesn't point up, so I don't drive it up. Doesn't point down, so I don't go down. Goes round and round. Ooh, did I miss something?
A reaction.
Kelly's popping me on.
Reaction there at the
your little reaction there. You're right. Goes way on up in the air to here. Thank you. Now I go straight across, and as I cross that moment, it doesn't go up like the reaction I missed did. Doesn't go down like the triangle did. Goes round and round. Well, this curve shear diagram has no place for round and round. Just goes right on across. Don't let it go up. Don't let it go down. It has influenced the diagram. It changed the reactions. Next, the block 4 times 10 drives the curve down. Next, the reaction drives the curve up. And finally, it drives the curve back down to 0. Next diagram would be your moment diagram. This is the area that we're going to use. Because the power of the curve is an x squared curve, the area under that curve, if you go back on the first day and pull your notes, you'll find the area is 2/3 the base times the height. That's the area under a fat parabola. That will drive the diagram down because it's below the diagram, below the line. The curve is a cubic. It's either this one or the top one. I go to the 0 end of the shear diagram's value. I come straight underneath that part and insist that the diagram have no slope at that point. That says the top curve is the proper curve. That little rule that the value turns into slope, very, very valuable. Next, moment diagram jumps up, or it slides up. Concentrated moments make the diagram jump down. Next, moment diagram comes up. Next, moment diagram comes up. Next, moment diagram goes down. Next, moment diagram goes up. Strictly because these are positive, 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 negative, positive. And the whole thing, may be shifted up or down somewhere on the curve, I don't know where, but that's basically the shape.
In your zero slope there at the reaction, at the wrong cubic there at the beginning?
This is a cubic curve,
Okay.
And because the one preceding was a squared curve, and because the one preceding was an x to the 1 power curve.
Right.
And was the question...
Oh, it's going to be a cubic.
Why should it be a cubic?
No, I understand why it's a cubic, but zero slope should be at R1 and not at the beginning, right?
You might think so, because it just might seem like that'd be a neat way for it to happen. But you see how you never say this, and this is what most people say. Slope tells me slope. Not true. Value tells you slope. So what you do is you go over to this shear diagram, and let me try and get rid of all the garbage that I played with trying to get the truth here. That's pretty much what this diagram looks like. It's a great big solid parabola, a fat one. You go to that parabola and you ask yourself which end is the zero end, and this is the zero end. So right underneath it, you need to give me a curve that starts with a zero slope. If you wonder where zero slope is, go get your skis and stand on this one right here, and then stand on this one right here, and if you scream and holler all the way down, that wasn't the zero slope. It's the other one was the zero slope. Now on the other end of the figure, see right here we have a tremendously big value. So right underneath that I want to see a big slope. And this curve is the one that has the big slope, the one that you kind of agreed on to begin with. Does that make some kind of sense?
All clear now.
Okay, great. All right, now what do we do with this thing now that we've got it? Page 22. Once we have found the biggest moment off of the moment diagram, we're ready to compute the magnitude of stresses in the beam and compare them with the allowed stresses. The stress equation, sigma, is the bending stress in the beam, is equal to the moment you get from the peak on the moment diagram. C is the distance from the neutral axis to the outside surface of the beam, and I is the moment of inertia. We calculated these quantities last time. For instance, a typical beam might be a wide flange. It looks kind of like this as seen from the end. You calculated the location of the centroid or the neutral axis that would occur in the middle. You wouldn't have to compute it anyway because it'd be in a book. Even if it's an angle, it's in a book. If it's a channel, it's in the book. It's in your tables. This is the distance C. How far is it from the neutral axis to an outside fiber? And then I is the moment of inertia of that beam. By the same token, you would not compute I for a standard rolled steel shape, you'd pull it out of the tables. And you should definitely take a pretty good set of tables in with you. Probably the AISC handbook is what you need, because they're all in there. The stress distribution looks like page 23. The peak stresses on the beam, let me draw the beam back here. Here's the beam as seen from the side. If it's a wide flange, you'd see a flange on the top. You'd see a web in the middle. You'd see another flange on the bottom. If you were looking at an end view of it, kind of like so. There's your neutral axis. You'll notice that the top and bottom fibers are the most highly stressed, and that's why they cut all this steel out of here. It was pretty much a waste, so they took it all and they shoved it up on the top and the bottom flange, and they leave just enough steel in the web to hold the thing together. Those bending stresses are bending moment, C distance, I moment of inertia. There's your C distance. Now there are also some stresses tending to collapse this web, and those stresses are shear stresses. They are not usually of very large magnitude, but they do still appear in the beam, and they have to be calculated. And they're given by shear stress. It's a wiping stress as opposed to an axial or normal stress as bending stresses were. VQ over IT. Most of the terms are very easy to come up with. V is simply off of your shear diagram. You already worked your head off getting that number. I is the moment of inertia of the beam. If it's a steel shape, you dig it out of the tables. T is how thick is the beam where your boss has asked you for the answer. And Q is the first moment of area above that point. Now, it's easy to calculate them, but it takes a little description here. On page 25, I've got a beam. This one happens to be rectangular. It happens to be 6 inches across the base. It happens to be 20 inches tall. My boss has decided to glue the pieces of wood right where that line is. And that line happens to be, this will be 10 inches, so I got 10 inches left here. This is 8 inches and 2 inches. In other words, this guy bought a piece of wood 18 inches deep, and he capped it off with a piece of wood 2 inches deep, a 2x6. And he came to me and he says, do you think that glue is going to hold? And I say, well, I don't know. There will be some shearing stresses at that section. He says, well, calculate how much shearing stress there will be at that level on the beam so I can go out and buy a can of glue that says 60 psi strength glue or 200 psi shear stress glue. You know, they got glues of different strength. So here's what I calculate. I calculate the shearing stress is equal to VQ over IT. The shearing force I'm just going to write that from the shear diagram. Because we'll pull it off of the shear diagram, whatever we get. The moment of inertia is the moment of inertia of the whole mess about the neutral axis. It will be base, 6 inches, times height, 20 inches. That number is cubed, BH cubed over 12. That's the moment of inertia of a rectangle about its own centroid, about the neutral axis. When my boss asked me for the stress on this line, I drew a wiggly line on the picture. The length of that wiggly line is T. However long that line is, that's what goes in this slot right here, T. So in our case, it is a 6-inch length. It's how thick the beam is at that level. And the last thing is Q. And here's how you get Q. You come up to the line where your boss asks you for the stress, and you crosshatch everything above that line, regardless of what it is. If it flares out after that point, you crosshatch it. If it gets skinny, you crosshatch it. If there's a hole drilled in it, you crosshatch the hole and subtract it. Then Q is simply equal to A1D1 plus A2D2 plus ... That's almost like you solved for a neutral centroid, a neutral axis previously. The only thing is you just do the A1D1 plus A2D2 plus A3D3. You don't divide by A1 plus A2 plus A3. So here's Q. For us, Q is equal to the area crosshatched is 2 inches deep. It is 6 inches wide, and the distance to the centroid is 9 inches. So Q is simply that number. There's only one area, so we only have one A1D1. It is the cross-hatched area times the distance from the neutral axis. 2 times 6 times 9, 12 times 9, 90 plus a few more, 90 and 18. 108?
Sorry, I was doing it all.
Oh, you're doing the whole thing? That's okay. 108 inches
yeah.
cubed. And doesn't matter what it is. Whatever it is, that's the glue you got to buy. That's how strong it has to be in shear. Okay, now there were several problems like that, especially in the timber section. In the timber section, there was a whole pot full of glue-lam beams. And, you know, when I say there's a whole bunch of those, I'm talking about in your notes, I'm talking about in the timber part, when the guy presents the timber part, I've seen his notes, in the sample solutions to problems that you got in the books. There's a lot of that stuff. Now, most often people will not be interested in the shear stress high up on the beam because they're not a maximum at that point. Shear stresses are actually a maximum at the neutral axis. So if you'll show me the neutral axis, I'll tell you that the beam is most highly stressed at that point. The only thing in a glue-lam beam, every line of glue is a line of interest. And so in a glue-lam beam, they may indeed ask you for the shearing stresses up in the air like we just solved on page 25. but most often you'll find the most important shear stress is at the neutral axis for a rectangle. Now if you go ahead and solve for Q for that, you'll find the equation for the maximum shear stress in a rectangle solves out to, all boil down to 3V over 2 times the area of the beam. It's just the terms in the moment of inertia get in with the thickness of the beam, get in with Q, and they all cancel out. And the maximum shear stress in a glue-lam beam at the center, if that happens to be a glue line, will be a point of interest, 3V over 2A. All right. And I was going to do another example on page 27. I had the load P, 2P was 60 kips, and the load P was 30 kips. The neutral axis solved out to be 1.6 inches above the neutral axis. And let me just say, you know, we can already draw a shear moment diagram. Q is the one we're kind of interested in. Here's how you'd get Q. You would crosshatch everything above the neutral axis. That would include two areas. You would then solve for Q is equal to a 1 inch thick piece has been crosshatched. That piece is 1.6 from 5 leaves me 3.4 inches tall times 3.4 inches tall. That's the area crosshatched. The distance from the neutral axis to the centroid of that piece is 3.4 over 2 because the centroid of a rectangle is in the middle. And there are two of them. So it's really pretty simple. Then the thickness of the beam would equal to, well, my boss asked me for the maximum stress. That's why I went to the neutral axis. And I put a wiggly line, and I put a wiggly line. And I crosshatched everything above the wiggly line. The length of the wiggly line is 2 inches, and that goes in the equation. V, I get it from my shear diagram. Q, I've already got it. The moment of inertia I can solve for, and the thickness of the beam. The moment of inertia, we did practice on that on the first sessions. All right, page 28 is more of the same. Page 29 is more of the same. Cylindrical pressure vessels are so simple, there's nothing to them. You just flat got an equation for hoop stresses and longitudinal stresses and the maximum shear stress in there. And I am going to kind of cut these next sections down because with a half hour left, there are a bunch of structures on the quiz, usually, that are statically indeterminate. And those structures are generally solved by some method of solving for statically indeterminate structures, and without that, you're at a pretty serious disadvantage. So I want to kick over to that, and then if I got some time left, we've got some sheets, you know, that I can show you. But if there's any sheets you can handle on your own, I can tell you cylindrical pressure vessels are certainly the ones you can do. Same way with page 31 is just shows you where those cylindrical where the cylindrical stresses act. Page 32 shows you spherical pressure vessel equations. Combined stresses just shows you what happens when you combine the stresses. I think the only time that I've seen something like that would probably be like on page 35, where you have some axial stresses in combination with some bending stresses. For instance, if you'll show that load P at a eccentricity E off of the neutral axis, then you get some sigma is equal to P over A stresses, and you have to add them with some sigma is equal to MC over I stresses, some combined stresses. That's a sheet I'll come back to if we've got a little time. Same way with 36, same way with columns. The equation for columns on page 37 is pretty straightforward. It's well covered in the book that you got. Deflections are pretty straightforward. They just come up under an equation on page 39. How much a torque shaft rotates or twists is on page 40 and 41. And page 42, deflections of beams. Be sure you take an AISC code in with you. You'll really find that's got a lot of good tables, especially for deflections of beams. Page 43 is combined stresses. We'll come back to that if we got any time. But I want to do moment distribution because it is absolutely going to be on there. I bet you. I haven't seen any of these things that they don't have some statically indeterminate structures on the beam. All right. Now, somewhere in here, I've got one already nicely worked out. I'll also send you some more of these worksheets, so if you like them, you can use them to compute these. Bingo. There we go. Chances of seeing this are very small, but you've got a worksheet, and I think you can tell which blocks I am marking in. So, I'm going to tell you I have a beam that goes from A to joint B to joint C to joint D, and get you to draw it for me. Here's the beam. It is pinned at A, pinned at B, pinned at C, and pinned at D. Take it back. It's got a wall at D. So draw me a big old heavy wall fixed at D. Now that kind of structure is statically indeterminate. It has more reactions on it than are needed, and the moments inside the beam are necessary to find or to design the beam. I'm going to put a uniform load on this beam of 2.4 kips per foot from A to B, and I'm going to put another load, same magnitude, could be any magnitude, 2.4 kips per foot between C and D. Now that structure has moments inside of it which are not able to be solved by statics alone. There's too many reactions. So what we do with the structure is we lie. We come to joint A and we pretend there's a guy with a wrench who does not let joint A rotate. We put a wall at joint A. We come to joint B and we do not let that rotate. We put a wall at joint B. We come to joint C and we put a wall. And we don't have to lie at D, there's already a wall at D. Now then, the structure is not loose to do what it would like to do, but at least it does something I understand. At this point, I can tell you all the moments inside of that structure. And the way you find the moments inside of that structure, I need a big old fat brown book from down there, Kelly. Forgot to bring that with me. There is a table of things called fixed end moments. That is it. Civil Engineering Reference Manual. You will find a table of beams with various and sundry loads on them that tell you how much moment a guy with a wrench asked to go out in the rain and hold those ends against rotation will have to come up with in order to fix the joints.
What page is
That's a good question. What page? Fixed end moments, page 13-5. So we look on page 13-5, and we find nothing. So much for the index, but we're in the right place because it says indeterminate structures. So we go to the end of indeterminate structures. They're on page 13-21. There'll also be a whole bunch of them in the AISC manual. There are some more of them on page 13-32. And I take it this is your old book, Kelly, because I see you got the page dog-eared. So it must have been one of those on a quiz, huh? All right. We want the case that shows a fixed beam totally loaded across its top. It's on page 1321. It's the fifth one from the top of the page on the left-hand side. See, somebody's already worked out that kind of a structure and found that the moment on the left end is a negative WL squared over 12. Clockwise moments on the beam are considered positive. And on the right end is WL squared over 12. So I'm going to calculate WL squared over 12 for our beam. I'm going to make our beam 12 feet long, 12 feet long, and 12 feet long. That says WL squared over 12 is 2.4 kips per foot multiplied times 12 feet, quantity squared, divided by 12. That calculates out to be 28.8 kip feet. And that is obviously, since both ends have the same moment on them, that's the same number on both ends. So what I'm going to do is, if you'll look in your table, you will find a thing called fixed end moments. Beam AB has a couple of blank spots in the table to enter the fixed end moments on each end of the beam. Next to A, I'm going to list minus 28.8. That's how much moment a guy with a wrench would have to produce in order to fix the left end of that beam, which shouldn't be fixed at all. It should be loose. On the right-hand end, since the moment is clockwise, I'm going to enter a number positive 28.8 for how much torque, how much moment a guy with a torque wrench would have to apply to the end of the joint in order to get the beam fixed on the right-hand end. BC, well, there's no load, so I don't have to look in the table. I simply put a 0 and a 0. CD is exactly like AB, so I'll enter minus 28.8. and a positive 28.8. Now, those aren't bad starts right there. Those numbers right there would be better than nothing. Of course, I really would have to leave the guy out in the rain for the rest of his life holding those wrenches for that to be the truth. So what I'm going to do is I'm going to start letting those wrenches go. And as I let them go, the stiffnesses of the beams will actually accept the moment that he lets go. What I need to know is how much of the moment released from joint A and released from joint B actually goes into each side of the joint. Now, to do that, at the top of your sheet you'll see some calculations that's called EI. That's the modulus of elasticity of the beam times its moment of inertia. And I'm just going to say I picked a beam which has E times I of 600. So you just enter 600 for EI. E would be, for example, modulus elasticity of steel, 2.9 times 10 to the 7th kips per, or pounds per square inch. Moment of inertia would be the moment of inertia of the beam from a table. And I'm going to make them all 600. Just to make, wait a minute, I take it back. I'll make the middle one 1200. So if you'll enter it as 1200, and the right-hand beam is 600. So the three squares, the three open squares there, read 600, 1200, and 600. Then you enter the length of the beam. That's 12 feet, 12 feet, 12 feet. If you want to enter 12 times 12, 12 times 12, 12 times 12, it won't matter. That's okay. Because these are relative numbers anyway. Now then, in your notes on page 44, 45, 46, and 47, it's got very detailed instructions on how to compute how stiff a beam is. And I'll let you read that, and we're just going to kind of summarize it. On page 44, it says, how do I compute K sub ij? How do I compute K sub AB, for example? Well, the stiffness of any member is 3EI over L. 3 is a constant. E is the modulus of elasticity. I've already got EI and I've already got L, so that's nice. They're already in the table. I just multiply 3 times EI over L. If when you stand at that joint and look at the other end, if it's pinned, it's 3EI over L. If, on the other hand, you stand at that point on the beam and the other end is not pinned, I don't care if it's a member connected to it, I don't care if it's a wall, it doesn't matter. If it's not pinned, then the K sub ij value is 4 EI over L. So when you stand at A and look towards B, there's a place here to be filled in. When I look towards B, the other end is not pinned. By that I mean it looks, there's a pin there, I admit, but the member goes on. The member doesn't stop at a pin. That might actually be better wording. K sub ij is 3EI over L if the other end of the member is pinned and quits and there's nothing else out there. That'd probably be some better words there. Write that down right quick. Nothing else there. Alright, so we have to compute 4EI over L. And 4 times 600 divided by 12, 4 times 600 divided by 12, that's a third of 600, that's 200. So I enter 200 in that slot. And that equal sign kind of needs to be scratched out. Those equal signs are just, they're trying to show you they're both for that beam. Because when I get down here to the left of joint B and look to the left, I do see a pin. And I do see nothing past that pin. And therefore the answer should be a 3 EI over L because of what I see on the other end of the beam. 3 EI over L would be 3/12 of 600. That should be 150. Now I go to fill in the hole just to the right of joint B. As I stand at B and look to C, I do see the beam continues on. It's not pinned and quits. Therefore, it's 4 EI over L. 4 times EI, 1200, divided by L is 12. That number is 400. And looking back, I get the same 4 EI over L, so that's 400. These numbers are relatively how stiff is the beam. These relative stiffnesses, the beam actually picks up moment when you tell the guy to let go of his wrench. It picks up moment in that proportion. As I stand at C and look towards D, I see no pin and quit. I see a wall, and therefore the stiffness is 4 EI over L. 4 times 600 over 12 is 200. And as I stand at D and look back at C, I see 4 EI over L, that's another 200. Alright, now I tell you what, we've got another couple of holes up here. Let's go up to the left of A. Up at A, I don't see anything but air. I put air. Over at D, I see a wall. So I'm going to write wall. How stiff is air? Well, air doesn't have any stiffness, so I'll put a 0 in that slot. How stiff is a fixed wall? It's infinitely stiff. So I put an infinity number for how stiff is a wall. Now the next line says, add the stiffnesses to the left and right of the joint, and there's some little arrows there. They're not very big, but they're supposed to kind of show you to go to the left and go to the right and add the two numbers up. And you get a 200 for the total stiffness at that joint. None because of the air, and 200 because of the steel member to its right. You go right under joint B and you see how stiff joint B is. You add the number to the left is 150 plus the number to the right. 550 tells you how stiff is the total joint. You go to joint C and you say how stiff is the joint? 600. And you go to joint D, 200 plus infinity is infinity plus 200. It's really stiff. And the wall would be really stiff. It wouldn't have much flexibility like a member would. Now the sets of numbers inside the black lines are numbers that you use in computation from then on down the table. The distribution factor is discussed on page 44. Tells you how to compute them. Basically, it answers the question, if a guy standing at joint A is holding on with a moment of 28.8 registering in his torque wrench, and he let joint A go, where would the moment go? How much would go to the left of the joint, and how much would go to the right of the joint? That is found by simply calculating the K value to the left of the joint. It's right up above, divided by the sum of the K, 200. So the answer is, how much torque, how much moment goes in the air? 0 divided by 200. That answer is 0. And for computational purposes, you'll be better off if you put a minus sign in front of it, because you're getting ready to multiply times that number. There are little minus signs in all of the cells. They're a little hard to see. They were real easy to see on a computer. Looks like that one down there is gone, but they all should say minus to remind you that something needs a sign change later on. Now then, the stiffness of the next empty spot here, you go up and get the K sub ij for that member, divide it by the sum of the Kij listed just below it, and 200 over 200 is 1. I really suggest you put a minus 1 in there to remind yourself to change a sign. You'll see that in a minute. The next stiffness is 150 over 550. That comes out 0.273. The next stiffness is 400 over 550. Comes out minus 0.727. The next stiffness comes out 2/3. Might be just as easily to write that down 2/3. Might have just been as easy to write this one as 15/55 rather than divide it out. The stiffness is 2/6 or 1/3. The stiffness is 200 out of infinity, that's none. The stiffness is infinity out of infinity, that's 1. The nice thing about this method is it's really confusing. It's really strange. It really takes some thought. Only in this region right here is it screwball. Once you calculate a couple of the numbers, man, you're on your way. 0 over 200, nothing. 200 over 200, 1. 150 over 550, that number. 400 over 550, that number. 400 over, and the little arrows tell you which ones go together. Those are your distribution factors. Now, when the guy lets go of his wrench, some of the moment that feeds off in that joint will slide down to the other end of the member. That's called a carryover factor. Carryover factors are discussed on page 45. But basically, a carryover factor is 0. I'm reading from the top of page 45. A carryover factor is 0 if you're going to a member that on the far end is pinned and quits. In other words, there's no more members. The carryover factor is a half if there is another member down the road, or if there's a wall. If there's anything down on the other end, the carryover factor is a half. So, I stand at joint A and look towards B, and since I see somebody down there on past B, the carryover factor is 1/2. When I stand at B and look at A, all I see is a pin and it quits. The carryover factor is 0. I stand at B and look at C, a half. I stand at C and look at B, a half. I stand at C and look at D, a half. I stand at D and look at C, a half. I mean, it's almost always a half. The only time it's not a half is at B when you look down there and see a pin. There is no carryover factor on that one. Now, one more time, if you look at this and say, this is a zoo, well, you're right. If you look at that and say, man, if I could just bring my computer in here, I'd use Strudel or RISA or one of these little structural analysis programs and bang these numbers out in nothing flats, what you do in the real world. Yeah, but unfortunately, they won't let you bring one of those in. Somehow you got to get these moments. And slope deflection, not easy. Direct matrix solution, not easy. You know, there's just no method that matches this one to get these forces inside the members. Alright, incidentally, in the air, there was no fixed end moment. I forgot to mention that. It's just air. In the wall, there was no fixed end moment. It's just a wall. The only fixed end moments came from the beams. Now, I want to find out how badly I've torqued this guy standing at joint A. So I simply add the fixed end moment to the left and the fixed end moment to the right, and I get a minus 28.8. That's the sum of the two numbers to the left and right of that empty spot on the table. At joint B, the guy had 28.8 to the left and none to the right. That sums, and I mean, you don't say, well, since it's right, do I subtract it? Since it's left, do I? None of that has to happen. It is flat. Add them up. At joint C, minus 28.8. At joint D, 28.8. The table is, you can't hardly go wrong. You just add them up. Next, I say, all right, person at A, you can go have lunch. He says, well, if I let go of this wrench, this 28.8's got to go somewhere. I said, yeah, it's going to distribute on either side of the joint. He says, all right, well, let me let it go here. He says, okay, that's a little less. All right, where's it going? Well, that 28.8 distributes to the left according to the distribution factor. You got to go all the way back to the black lines to find out how much it distributes. To the left of the joint, it distributes minus 28.8 times the distribution factor. That's what the rule in the column says. Minus 28.8 times a minus 0 is 0. Well, that makes sense. None went in the air. To find out how much goes to the right of the joint, you multiply the minus 28.8 times the distribution factor given above. That's positive 28.8. Now, most books won't tell you the distribution factor is a minus 1, because it's really not. It's the fact that he lets go of the 28.8 that changes the sign. Not truly because you multiply it times the distribution factor. The only thing is I can never remember to change the sign. So if you put the minus on the 1, you'll see 28.8 times a minus 1, and you'll get a plus 28.8. It's what happens when he let go of the wrench. All right, let's go for what happened when the guy at point B loosed up on his wrench. 28.8 times a minus 0.273. That's easy. All I do is crank it on a calculator. 28.8 times minus times 0.273.
It's minus 7.9.
Minus 7.9. And 28.8 times 0.727 is?
Minus 20.9.
Minus 20.9. You'll notice that those two numbers add up to the original moment the guy let go of. And if they don't, then you got a mistake. Because when he let it go, it all had to go somewhere. Next, 28.8 times the distribution factor of minus 2/3. A minus times a minus is a plus.
So it's 19.2.
19.2. Thank you. And 28.8 times a minus 1/3 is a positive
9.6.
9.6. Let me see right quick. 6 and 2 is 8. 9 is 18. That's right. And add a 1. That's correct. That adds up to the original 28.8. 28.8 times none is none. 28.8 times a minus 1 is a minus 28.8. Now, when this 28.8 came into this member, some of it probably went across to the right. Because normally when a guy cranks on one end of the member, some of it travels across the member to the other side. You can find out how much of that happened by looking at the carryover factor directly above the 28.8. 28.8 times a half carries over. This should really be a great big nice arrow pointing like this. This ought to be a great big arrow pointing that way. I just flat couldn't make the computer do what I wanted it to. Wouldn't draw big arrows. So probably ought to fill in some arrows there. Half of 28.8 goes to the right, 14.4. How much of the 7.9 carries over to the left? You look directly above for the carryover factor. None. Well, that actually makes some sense because there's a pin over there, and so none of it can get to the pin. The pin wouldn't take any moment anyway. Carryover factor on everything else is a half. Half of 20.9, 10 point, phooey on this decimal point, 10.5. I'm not about to write down 10.45. The initial number didn't have that much accuracy, because then I'll be taking it down to 5.02613. You know, that's ridiculous. There's no accuracy in those numbers. Half of 19.2 is?
Okay, you're 9.6.
Half of 19.2 is 9.6. Half of 9.6 is
4.8.
4.8. Half of 0 is 0. That's pretty easy. Next, I have some really bad news for you. At joint B, 14.4 slid over when guy A let go of his wrench, and 9.6 slid over from joint C when that guy let go of his wrench, and the two add together, causing some more imbalance in joint B. So the guy at joint B didn't get to go home after all. Just about the time he let go of everything, some moments come sliding in from the other ends, and he's now got the sum of those two. 6, 9, 10 is not carry 1. 9, 10, 11, 12, 13, 14, carry 1. He's got a 24 moment in his wrench. He says, whoa, what am I supposed to do? I said, I don't know. Don't go home yet, though, if you've got 24 in your wrench. Joint A is kind of nice. You add the moment to the left, you add the moment to the right. There wasn't even a place at the left. There isn't any. He doesn't have any torque in his wrench. The guy standing at joint B says, well, things are better than they used to be, but I still got some torque in my wrench. I say, how much? He says, 10.5. I talk to the guy at joint D. I say, have you got any torque? He says, yep, 4.8. You merely add them up. I say, well, man, I don't know what went wrong. Let's try it again. A, let go of your wrench. He says, okay. I say, how much went to the left? 0 times 0, 0. 0 times minus 1, 0. He says, nothing. I say, all right, I like that better. I go to joint B and I say, let go of your wrench.
I have a question real quick.
You bet.
Okay, that 10.5, shouldn't that be negative?
Yes.
Ha! Sure glad somebody knows what they're doing here. Thank you. What are you doing here?
I'm watching the numbers over
Oh,
here.
yeah. You're watching the numbers over there. Okay, any more sign errors there?
Let me check.
Actually, we do have it worked out. And actually, we could have transmitted it to you already worked out. I just tell you the truth, I don't think it's easy to learn if your hand doesn't write something down. It just doesn't get to your brain as fast. All right, looks good.
Yeah.
All right, now then, the guy at joint B lets go of his wrench, and we let go of the 24. 0.273 of it hooks it to the left, and if you'll notice the rule over on the left-hand side, it says, multiply the out of balance, that's the 24, times the distribution factor from above, and that gives us
minus 6.6.
Minus 6.6. And sliding to the right of the joint gives us
Minus 17.5.
minus 17.5. We then tell joint C to let go of his wrench. 10.5 times 2/3 is a plus
Turns out to be 7.
7.0. And on the right,
3.5.
3.5. And the 4.8 guy lets go of his wrench and feeds off to the left. 4.8 times 0 is none. And 4.8 times a minus 1 is a minus 4.8. And the sad news is this never quits.
Turns out this is a minus right there.
Oh,
Also.
I got a minus mistake on that one too.
Yes.
Thank you, because that's a carryover. A carryover of 20.9 carries over to a minus 10.5. And then a minus 10.5 and a 0 gives me a minus 10.5. Thank you. But it doesn't matter that it never quits, because it very quickly goes down to 0. So let me just feed in the numbers. I think you see what we're doing. We're carrying over the carryover numbers, and we're distributing the distribution factors. So on the bottom of the page, the numbers read those off to me and I'll write them down.
Well, a little bit second here.
Yeah, that one's got different lines on it, so let's go to this one. We're at this level right here. Just read me those, and
0.
0,
0.
0,
3.5 positive.
3.5,
Minus 8.8.
minus 8.8,
0.
0,
1.8.
1.8. All right, then those would be distributed. No, that was the distribution. Now those will be added to check on the imbalance. And we get
0.
0 on the next page.
3.5.
3.5.
Minus 8.8.
Minus 8.8. I can see that happening right above me there.
And then a 1.8.
And a 1.8. All we're doing is adding the numbers above. Then they're distributed. 0 and 0, obviously. How does that 3.5 hook it off on each side?
Okay, minus 1.0.
Minus 1.0.
And a minus 2.5.
A minus 2.5.
And then 5.9.
5.9.
And 2.9.
2.9.
0.
0 and a minus 1.8. Or is that a plus?
That's a minus.
Distribution, that's
Yeah.
correct. All right, so I can get rid of this table above us. It's still good, but it doesn't have any need for me to fill in. All right.
There'll be 0.
None carries over.
And then another
None
0.
carries over.
3.0.
3.0, that's half of 5.9.
Okay. And then minus 1.3.
Minus 1.3.
0.
0.
And 1.5.
1.5, okay. And let's just feed them out. Give them to me. Out of balance.
0.
0.
3.
3.
Minus 1.3.
Minus 1.3.
And 1.5.
1.5. All right, read me the distribution for number 4.
0.
0.
0.
0.
Minus 0.8.
Minus 0.8.
Minus 2.2.
Minus 2.2.
0.9.
0.9.
0.4.
0.4.
Minus 1.5.
Minus.
That's a 0 there.
That's a 0.
Yeah.
Okay, I agree, because none comes this way and minus 1.5 goes into the wall.
Right.
All right, now I've got a few numbers, but I don't care, tell you the truth. The numbers are getting so small now, it probably is not going to matter much.
Okay, you want to go to 4?
I'm just going to go ahead and show them what to do. The final answer, this process probably should be carried a little further. The final answer is you do nothing but add up everything in sight. The final moment on the last page, a lot of times you don't use all 2 or 3 pages, because the numbers close out pretty quickly.
0.
0 for the final moment,
0.
0 for the final moment. Well, that's on each side of a pin, so that makes a lot of sense. There shouldn't be any moment in the pin.
26.7.
You get a 26.7 in this member.
26.8 minus.
26.8 on this side, and that's a minus. See, that's on either side of joint A. Were it a perfect world, those two numbers would be the same number. All right, what do you get in this slot?
11.7.
11.7 and a minus 11.7, I hope.
11.9.
Well, nothing's perfect. 11.9.
And then 37.3.
37.3 and a minus.
That would be the wall,
That's how much is in the wall.
which is.
I didn't write it down, so you can't tell me. But it ought to be somewhere around 37.3. I did forget to add those up,
That's correct.
so I could care less. My last point is as follows. Here are your answers. Beam, as for an example, beam CD has those moments on the end. Here is the beam. It has a moment of a minus 11.9, which is a minus, means it goes this way, and the bending moment is 11.9 kip feet of moment. It has a uniform load across its top, and that load is 2.4 kips per foot. And it has a moment on the right-hand end positive, and therefore that is 37.3 kip feet of moment. You draw a shear moment diagram for this dude just like you did for everybody else. You use statics to solve for the reaction on the left and the reaction on the right. You come down and draw shear and bending moments for that beam, and you have the maximum shears and moments to be designed for. Now, I guess it's why they give you all day to take the quiz, because you see this could get to be a time-consuming process. But there are definitely some problems on there, almost invariably, that require you to get the moments. And I know they could care less how you get the moments, but it's got to be done somehow. All right, we already kept you 15 minutes over. Rob, what do you think?
I think we're good.
You think you're numb?
Magic.
All right. Rob, Ramsey was going to kind of pass around a sheet and see who could use an old statics book, who could use an old strength of materials book, who could use an old structural analysis book, you know, with moment distribution in it and stuff like that. If you, yes, sir. Yes, ma'am.
Ramsey's not here, but I am Rhonda Bro. I'm
Okay.
the facilitator at night, and I have Ramsey's sheet if you want me to pass it around.
Well, it doesn't matter to be passed around right now because the quiz is not for a while. What? Yeah, we'd like
Okay.
it passed. We'd like it passed around to the people who came tonight, the people who would rather went out and drank beer tonight rather than come, the people who are going to come tomorrow. If you can just kind of total out how many of those things I need to round up. Also, if you would add on that sheet, anybody want to see tape video that Kelly bought? Let's go up on this other. There you go. Kelly bought a pretty nice set of tapes put out by ASCE, and they cover everything we're doing too. And if anybody is interested in those and has the time, I'll send that set of 12 tapes down and with the books.
We definitely would look at it. That's
All right, well then I'll definitely ship it down to you. Now Ramsey said he might be up this way, in which case it'll save us the shipping if he gets here. If not, Rob how about if I just, or I guess to the facilitator, either one, I just know Rob now. But, you know, somebody that I know and trust, try and get most of them back after they take the quiz in about 3 months and study these like crazy.
Sir, if you want, we can keep them in the lab for you.
It's really not, let me look here. No, they all have honest faces. If they want to take them home, let them take them home. That'd be fine.
Okay.
And the books, of course, the books will go with them without a doubt, because no sense
Okay.
in, if those get lost, it's no big deal. The publishers are dying for you guys to see them and maybe want to go buy one of your own, so they'd love that. Okay, been fun. Anybody got any questions? They're supposed to set me up an email account. You can give me that overview again. You can give me a call. And I guess you probably already have this from the other night. You can reach me there. You can reach me at email, LLL2761 at zeus.tamu.edu. And really, when you work on some of the stuff in the book, you say, I have no idea. Where did you get this stupid number? Is that Zeus right? Z-E-U-S or Z-U-E-S? I bet that's Z-E-U-S. I've misspelled that. I don't know why they give these things Greek god names.
On that Zeus, talking to the people that have the props over there, they're interested in finding, apparently that should have a number associated with it. Is there somebody we can contact to make sure we can find out what that number is?
Are you able to go to straight internet addresses?
Well, up to a point. Apparently they have to load the information on our computer, connect with your computer, and they say that Zeus is a name, that's fine, well, and good, and as soon as they know what the number is, get the translation.
Okay, well,
They thought they could contact you directly at tamu.edu, but I tried, it didn't work.
all right, how about trying
I tried
this?
both.
How about trying LOWERY at tamu.edu? Now we
I tried that also.
You did. All right, then I will get you the number.
Well, that's probably our computer, though.
That's okay. All these machines definitely got a number. You know, it's something like 198.192.17. something. I will I'll find you that number. Oh, I know my number. Oh, I hadn't thought about that. Yeah, my number is 128. 128.194.192.4. Is that my number? Phooey. Gee, I thought I'd remember that forever. What a mundane thing to remember. I will get you that number. I will have that number available to you tomorrow night when we come for the next one, and if you'll just have somebody pick it up, I will make sure I get that. That's probably the number right there. I believe that's correct. Do you remember those numbers?
If nothing else, we'll try to make contact through our Director of Information Management to figure it out.
All right, that sounds good. I'll either get you that or a phone number for the guy where this is at, because I think that'll really be quick and easy to shoot those email addresses or messages back and forth, and they're free. They're pretty nifty. Okay, any questions?
Yes. On that reference material,
Yes, sir.
if you're not necessarily taking the test this coming April, but sometime in the next couple years, but you still have a need for these books, should we contact you at a later date or attempt to get those books now?
No, you're more than welcome. 2 years from now, you hang on to that name. I've been here 35 years. I plan on staying another 35. My students call me up all the time, really, and say, gee, I need this book. I said, what'd you do with yours? He says, well, I sold it the minute I got out of your rotten class. I send them a book. Be happy to send you one. And all you got to do is just give me a holler.
Great, thanks.
Okay,
Got any AISE handbooks?
I sure do. I got a bunch of old
Yeah.
ones. They probably wouldn't be the most current ones, because I teach out of the current ones, and they're $80 a piece. I've only got one, but I definitely have an old blue one. I got an old red one. The member properties would still be the same. These tables that we showed you, the fixed-end moment diagram tables, tell me how many of those you need, and I'll send you down as many as I got.
Thanks.
Okay. Good night, gentlemen, ladies. See you.
Fine, thank you very much.
I just wanted to tell the class that there's going to be 2 makeup sessions for that one that we missed. It's either going to be on Friday, the 17th of February from 4:30 to 7:30, or it's going to be on Tuesday, the 21st, regular time. No, this is probably going to be videotaped. Friday the 17th, 4:30 to 7:30, or Tuesday the 21st, regular time, 6 to 9. Huh? Just put a little dash if you need those. This is Rhonda Bro. I need to speak to Gary.
What's that? Go ahead.
I was wondering about Thursday, tomorrow.
Yeah.
Do I need to call about a quarter till 6 on your cellular phone, or should I just try to dial up?
Just go ahead and dial up. I'll have it ready by 5:45.
Okay. So, is that how we'll handle it each time? Just a quarter till and go ahead and dial up?
Well, yeah, you could try that, but, or try my cellular, whichever. Sometimes I'm tied up doing other things, have 3 or 4 things at the same time, so, you know, if you call in and it doesn't come up, just try my cellular.
Okay. Okay, I'll do that. Okay, thank you very much.
Yeah, have a nice night.
You too.
Could you put up that worksheet, the very first page again?
You want the worksheet?
Yeah, first page.
Oh, okay, the first page on the worksheet?
You want to see it? What?
Yeah, he wants to put it up on the document.
Page 48.
That one right there?
Yeah, I was in the back of the class. I don't think I could see it as well.
What part would you like for us to zoom in on?
OOBI number 2, the summation of FEM equals FEM.
Okay, we'll see if we can zoom in on that a
Number
little
5
bit.
from the bottom.
Okay, is that any better?
Is that even the right place?
Go down.
Yeah, okay, we've got a 0 and then a... Right here?
Oh, that's a plus. I want the plus one.
Can't see the heading to see where we're at.
Move it to the left a little bit.
So we can see what line we're
That's
on.
good. Oops. Come back a little bit. That's good. Okay, that was 0.
Okay.
24. That's all right. 10.5.
10.5 and 4.8.
That was a mistake. I should have gone ahead and sent them a copy of that and left one of them blank for
You've
them
got
to work
this
on.
as 0. That's my problem there.
There's where it is.
And that's 14.4.
I'll definitely do that next time, but I won't get it done tomorrow
9.6.
because
This is going to be a duplicate class for us tomorrow.
it's a different group of people.
0.
And that should have a number.
Yeah, I'm trying.
Yeah, you're okay there. It's the next one.
0. Where was I? 12.5. 10.5. 10.5. 0.
It's got to be hard. I don't even see it.
9.8. There we go.
Hey, they're all right in above you.
That's better.
Got it.
Thank you.
Okay, sorry I didn't send you this with the answers in it. I was thinking we would, be able to do it that way. I've got the answers here, and I should have, and sure will do that next time, so you won't have to work so hard to get them like that.